Hey there, folks. Happy Friday. Today's problem is a really short one. There's no numbers or calculations involved. Rather, it's just a few lines of algebra on some variables, and then we're done. Let's take a look at a picture of what's going on here. There's this solid disk that's rotating about an axis through its center. We're told that we have to glue a mass to the rim of the disk at the end of a horizontal radius, which gives us two locations to choose from. We can either glue it here on the left or here on the right. Let's pick the spot on the right, this one. Next, we're going to release this whole thing from rest, which will cause it to rotate in the clockwise direction. Now, if we call the bottom point of the disk down here y is equal to 0, it would mean that the initial vertical position of this mass is at y is equal to r. The goal is to let this compound object rotate until the glued mass reaches the final y position at 0. And we want to solve for the angular speed that's shared by both objects at that point. Now, there's a really quick and easy way to solve this if we use energy methods. And remember, we should always try to use energy methods over other techniques whenever possible. Let's give it a shot. Here's our familiar energy conservation equation. There's a couple things that we can get rid of. Everything starts from rest, so there's no initial kinetic energy. That goes to 0. We're not told about any frictional interaction or anything else like that either, so the other work term will also be 0. On the other side of the equal sign, we said that the glued mass will reach a final y position of 0. So it won't have any potential energy left at that point. So this is all that's left from the line at the top. And to make it a bit more clear, I'll rewrite it using some specific subscripts. So we can see that the potential energy of this glued mass on the left is going to be converted into rotational kinetic energy for both objects on the right. Let's go ahead and insert the definitions for those next. The moment of inertia on the right-hand side is going to be the sum of the moment of inertia of the disk and the moment of inertia of the glued mass. And speaking of that glued mass, we weren't provided any details about its geometry. Typically, in that scenario, you're allowed to treat it like a particle. So that's what we're going to do here. Recall that the moment of inertia of a disk is 1/2 mr squared, and for a particle, it's just regular mr squared. Let's insert those next. We ultimately want to solve for omega on the right-hand side. So let's work our way towards isolating it. I'll multiply both sides by 2 in order to get rid of this fraction outside the parentheses. And with that complete, we can now combine these similar mr squared terms inside the parentheses. And 1/2 plus 1 is equal to 3/2. A factor of m on both sides can be eliminated, as well as a factor of r. Now let's multiply both sides by 2, then divide both sides by 3r, and then take the square root. And take a look at that. We're done. That's it. That's all we needed to do here. This problem is just a little practice on using energy conservation in a rotational context, and we'll see a bit more of that in the upcoming problem. Thanks for watching, folks. I hope you all have a great weekend. Take care.